Hello and welcome to this video about unit testing, and as you may notice, this is part 1 out of 2 planned parts. So let's move along. This is what we're going to go through in this 2-part series. So we will in the first part get to around here. That's mainly theory, and then down here we get a bit more practical about how to apply the theory and how to use the tools that we will introduce. So we're going to talk about what is testing in general. I know you will encounter this topic in the software engineering course as well. I have a little bit another note here. So we're using unit testing, and the software engineering course might be focused on different type of testing. So 2 angles on one topic, but still slightly different. I have a little motivation about why do we even want to test. Something about what is unit testing, because that's what we focus on here. You will see unit testing and integration testing and scenario testing, or maybe acceptance testing. Maybe you will hear about those other types of testing in the software engineering course. We are mainly focused on unit testing here. And we have some testing approaches. So this is theory about how do we define our test cases. Then there is a Java tool, the JUnit, which is what we're going to use. So basically, to put it short, unit testing is about writing code that can test your code. And there's a tool to help us do that, which is called JUnit. So we will look at, in the second part, how to create these JUnits, how to structure them. I will go through an example. We're going to test a queue. I hope you know what a queue is, otherwise you have to look that up first. But it's a collection similar to Java, array list in Java. Just another type of collection, slightly different functionality. So maybe this point here is not really being discussed that much in this video. And then finally we're going to take a look at how we can approach testing when we have an MVVM structure, because the MVVM structure, one of the driving points behind inventing that is to make it easier to unit test your system. So we're going to try to apply that. Okay, so back to the first point here, a little motivation. So just to give you a short introduction on why we should test. So this is Curiosity, a robot sent to Mars to take samples and find life on Mars and whatnot. And I have some links about how the guys who wrote the software did not test the robot correctly. So occasionally it breaks down and they have to do a hard reset from home, and that's super inconvenient. I'm fairly certain they are a bit disappointing that didn't do their testing thoroughly. And the same thing is true in your future. Maybe you're not sending robots to Mars, but if you ship a product to customers with broken code that you have not tested thoroughly, then that can really cause trouble for you or your company. So I'm sure the NASA guys felt a bit stupid here. Maybe they learned something from it. All right. So the point about testing is that you want to verify that your code works as expected. That's probably your approach on the first semester, right? You would insert some data and maybe into a method and something like that, and you would, give it a correct input and verify that it worked as expected given that correct input. So that is the sunny scenario. You're giving the right thing and you're getting the right thing. In the rainy or cloudy, or I don't know what you want to call it, you are somehow trying to do what is not expected. So this here, the sunny, is about testing that it works as expected, and the rainy part is more about testing that your system is robust. So if the users do not use your system as expected, or give it wrong input, or somehow do something they're not supposed to, does your system just crash and burn, or can it actually recover from incorrect input? I know we haven't discussed exceptions much, but I often see that students will just whenever something goes wrong, they will just not handle that exception, and then their program will crash. And I don't know if you've tried that yourself. One of your programs suddenly stops working and just shuts down, and that's super annoying. So it would be nice if those developers wrote their program in a way that it could recover from errors. Right. So we both verify that our program works as expected, but also that it can handle unexpected and illegal actions. Right. So again, I often see that the tests are mainly about the sunny cases, but we need to test the other thing, because these are your users, and your users will try to break your program in ways you cannot imagine, and they are in general fairly stupid. Right? You may have designed the most intuitive program ever in your mind, but once you get other people to try it out, maybe you'll get your illusions broken. So we want to create a robust program. Right? Obviously, he should have one of those cups that can tip over and just stand back up, one of those baby cups, so that doesn't spill. Right? So this cup program was not written in a robust way. There could have been improvements. Maybe this is an exception being thrown and everything breaks. That could be an analogy. So I also want to reference this guy. This is Edsger Dijkstra. You'll encounter him again later on. He's done quite a few things in computer science. And he has this quote that I found somewhere. Program testing can be used to show the presence of bugs, but never to show their absence. Basically saying that you cannot prove that a program is 100% bug-free, but you can try to find those bugs that you have. Again, trying to drive home the point that don't just give it the input that you know works. Try various types of input and see if your program can actually handle something that you may not have anticipated initially. And to put it shortly, we often want to try to make our program fail. Right? That's the rainy scenario, and I'm putting emphasis on the rainy part because that's often neglected. I see that from my students. So that's sort of an introduction to the motivation, right? We want to test our program because shipping broken programs will cost us a lot of money and customers and so on. And we also want to do this in a structured way. So in your first semester, your approach to testing first semester approach to testing, what I see most is some kind of main method. In my case here, I'm testing a queue, which we'll do later on. And I will just call a few methods sort of randomly, haphazardly in the main method, print something out and sort of verify the print, that I print out what is expected, and then I get to this point, okay, nothing is on fire, it's probably okay. But this is very unstructured. Right? There's no real structured approach to your testing, you're just randomly trying to do things. So you have not analyzed your testing, your test cases, so this is a very loose approach that will not get you very far. Another thing is if you test some program with a UI and you have to insert something and click various buttons and check marks and insert more text and whatever, and click a button and see that you get something, and you have to test another case, can I also insert something longer, or click other buttons, other check marks and press update, and it can quickly become super tedious if you have to test something, test some functionality through the UI, and then you find an error when clicking randomly around and you have to fix it, but do you then remember how to actually reproduce that error? Can you find the error again? And when you have fixed it, then you have to test the same case again. So can you actually reproduce that result and see that it is now fixed, right? So the sort of random approach, unstructured approach, is not very convenient, and it won't be useful in the long run. So we need a structured approach, and I have a small comment about sometimes you will work in a larger company, and you may do some testing yourself. But at my previous job, we also had a separate department which did some testing. And I would write some code and hand it over. I'm saying, okay, I'm not now done with my code. I believe it works as far as I have tested it. And I will hand it over to the testing department, and they will test my code, and then they will get back to me and say, we found these bugs. If I give it this input, it doesn't work, and so on. So they would write a strict, structured, data detailed chart for me to go through my test step by step. So that's basically sort of the same thing we're looking for when doing the unit test. Also a structured approach so that we can reproduce our tests and reproduce both errors and successes as we need to. All right, bit of an introduction here. So let's move on to the actual topic, the unit testing. So I mentioned we have different types of tests. You may have seen this V structure where you sort of design going downwards, and then you code and you do some testing. So you start coding, and the first test you do with coding is unit test, because that tests the smallest amount of code. Integration testing is then you put larger pieces of code together and test that they work together in collaboration. A system test is testing probably by feature, so you test an entire feature. Can it work from GUI to database and back again? And acceptance test is usually done by the customer, making sure that their test, the ones they defined, actually succeeds. So what you will be doing in your semester project is mostly unit testing and integration testing and scenario testing. Scenario testing is somewhere up here, basically taking a use case scenario and testing that. So either a scenario or feature or user story from the user point of view. So you pretend to be a user and test it. And integration testing is testing that certain classes collaborate correctly. And we can do that with the JUnit tool as well. So it's also worth mentioning here, and that's actually what we will do in my last example about the MVVM. That's integration testing, because I am testing both the view model and the model. So multiple pieces of functionality, multiple classes working together. That's the integration testing. In your semester project, you might write unit tests that test the database or client-server connection. These tests are a bit more complicated and elaborate, which I will come back to, but it can be done. I have seen some very wonderful examples of how to test the database using unit tests. You just have to be very careful about your approach and how you do it. All right, so the scenario testing, or the top part here, is mainly covered by the software engineering course. And that's also what I expect that you, based on experience, that this is the primary testing approach in your semester project. Unit testing is usually for more complicated logic calculations, that kind of thing, and we just don't see that very often in the semester project. So this is the one that you can always do. This one, always do scenario testing. Unit testing, it requires that you have some complicated code to test, otherwise it might just be a bit boring. Okay, so we get to the unit testing, and basically you write code that tests your code. That's the point of it. So we want to test the smallest parts of our system down to single methods. I have, for example, a method that can calculate some date or whatever, or some number, and I want to test that method given these inputs. Do I get the expected output? They are usually interesting for slightly more complicated logic. Okay, so just to sort of have a common understanding of what we're talking about, I'll just quickly show you what a unit test might look like. Hang on. Okay, so we have here in IntelliJ, I have my test class, bound array Q test, and I have, for example, a method that tests something, meaning that I try to put something into the queue, and we use some asserts. That's a tool that we will get back to, but basically here I verify that the size of my queue, I have put 3 items in, so I expect the size to be 3, and if the size is actually 3, then this is okay and my test will continue. Otherwise it will show an error here. So I have these assert tools, and there's a fail tool, and I have some various things that I can use to write these testing methods. So I have a bunch of these methods. I'm testing the enqueue methods in various ways, and basically it results, I'm just testing a fairly simple collection, but it can result in many tests, as you can see here, and I don't think I'm even done. So you can be very thorough in your unit testing if you choose to. Okay, but this is basically what it looks like. I have written some code that tests my code, the simple bounded array queue correct apparently, and this is actually something that you will be doing in your exercises as well, I expect. Okay, so back to the presentation. Here we go, and let me just find my beloved laser pointer. Zoom. And we have the unit testing. Okay, so that was the quick example. I have written some code that can test my other code. That's the idea. So a huge benefit of these unit tests is that you just have them. Once you have written them, you can always rerun them. You just click the run button and it will take a few seconds, and then you verify that everything that you have tested and have working up until now, it still works. So if you modify your program a little bit, you can just rerun your tests and make sure that you don't break anything. If all your tests go through, then you can probably assume that your new change didn't break anything. So a common approach in larger firms, I believe, at least we did it at my previous job, is just to have, whenever I would commit something to GitHub, or we used something internal but similar to GitHub, they had thousands of unit tests that would just automatically run, and I would get an email half an hour later saying if I broke any of the existing code. I had a study buddy who worked at a different place, and they would just automatically run unit tests every midnight, and they would get reports they could read in the morning to see if they had broken everything or anything at all. So it's a simple tool. Once you have written your test, you can always just rerun them, and that's what I talked about earlier, that you can reproduce your errors. So if you find an error, you write a unit test to verify it, and if that unit test fails, you try to fix your error, and you can rerun your unit test, and hopefully the unit tested now will then become green and indicate that the bug has been fixed. So that's the unit testing. We write code that tests our code. And you saw that I had a bunch of methods in my unit test class, and I have arrived at those methods using these theoretical approaches on how to write or define the test cases. So we have the black and white box, which is thought of a header to schools of testing that you just need to know about. So it's all tests can be done with either black or white box approach, most tests at least. And we have something about boundary analysis and equivalence partitioning, and something about SOMP. This is actually zombies, so there's an IES, but the IES is sort of fluffy, so we'll focus on this part. So that's the next step. All right, so black and white box testing, it basically depends, well, first on what kind of information is available to you, and then based on your approach to testing. So these are the two umbrellas that you can put all kinds of testing beneath, basically. Right. We'll start out with black box testing. So you should consider this your software. So this is could be from a user point of view. When a user tests your software, they have no idea how it works internally. They cannot see the code. They have no access to it. They may not even understand it if they were to look at it. So the software is just a black box. You can give it some input and you get some output again. And that's just what you can you can verify. So you don't have access to the code, you can see how it works under the hood. So that means you need to test based on the requirements, based on documentation, which is usually an elaboration of the requirements. Sometimes there's a specification. At my previous job, whenever I did a new feature, I would write documents describing how to use that, and what are the valid input and what are the expected outputs, and basically how to interact with the system. So those were also considered documentation, and that could be used to structure your testing approach. So black box is just you give it some input, you expect some output, and we do it from a user point of view. Meaning that you as a programmer can also do it, but you do it with focus on these here. This is also often the scenario testing, the acceptance testing approach, user point of view. All right, we can do unit testing with a black box approach. We can also do it with a white box approach, which is the next slide here. So white box testing, as you might have guessed, we now have access to the code. It's from a programmer point of view, meaning that if you have access to the code but cannot read it, it might still be considered black box because the code doesn't give you any valuable information. But white box, you can read the code, you can see where all the nooks and crannies, whatever you call it, the places in the code where you might expect something could go wrong. So you have to be extra careful about testing that. It can give you extra information about how it works, so you can design your test cases more specifically. So white box testing is from a programmer's point of view. We have access to the code. Right, I can see into the system, and because I can see into the system, we can apply branch testing or condition or decision coverage, meaning that if there is an if statement, then I need to test when that if statement is true, what happens. I need to test when that if statement is false, what happens. So that's the branch. There are multiple paths through your system, and each if statement is a branch in your system. So we need to cover all the branches. Well, in theory, maybe not always in practice. But the decision coverage here, if I have an if statement, I may need to, so I can see here specifically in my code that I need to check what happens if the count variable is equal to the cap variable. Okay, I expect this exception to be thrown. Maybe that's something I should test. If it's not equal, then I do not expect this to be thrown. So this is a fairly simple case because not much can go wrong here. But if there was a method call here that would return something or modify something, maybe that would be more interesting. So there's a branch here. Either the if statement is true or it's false, and different things happens. So to sum up, the black box, we cannot see the code. Usually it's from a user point of view, and we have to follow the specification, the requirements, and the documentation. The white box approach is we have access to the code, and it's from a programmer's point of view. And most of the test variations can be applied using both a black box or a white box approach, or both. Sometimes there is a gray box approach, which is a mix, but I don't know if you can halfway mix it. If you have, maybe you have access to part of the code but not all of it, so you white box some of it and black box the rest. So we can unit test using both a black box and a white box, but usually it's a white box approach. It's the programmer that writes the unit tests for his own code, but you might end up in a case where you want to unit test some kind of third-party library, for example the JDBC jar file or some jar file from JavaFX library. You might want to unit test that, and you cannot really look into the code. You can just read the API documentation, so you can unit test that using a black box approach. So it can be mixed if you want to. Okay, so these are the two umbrellas, and it just gives us a vocabulary to talk about our testing approach. Now it gets a bit more theoretical on how we actually define our test cases. So the question is, how do we approach testing a method? How do we figure out what to actually write in our unit tests? And I've mentioned the branch testing, that you have to cover if statements and loops. You can read these if statements, see what happens if Q is null, okay, something is done. What happens if the argument is null, something is done. Count equals capacity, we saw that, something happens here. So there are branches here that we may need to test. I know you may be confused about the T. That's not something you have to worry about. Just ignore that. You could consider it to be a string or whatever. T is just a placeholder. Something called generics, which you will see on third semester. Okay, so I hope the branch testing makes sense. It just means we have access to the code, and from the code I can see I might need to test various if statements. Next part is that some methods or some kind of functionality have what we can define as borders in their behavior. So I have a couple of examples here. Let's assume that you're making a web shop for a pizzeria, and you can insert a number. How many pizzas do I want to order? And the question is, can I order 0 pizzas? What happens if I insert 0 here? You as a programmer may think that doesn't make sense to order 0 pizzas. But again, remember that your users are potentially extremely stupid, so you may need to test that. So that's a border, right? Maybe you are allowed to order between 1 and 10 pizzas. So 1 to 10 is the valid range, and everything outside is invalid. So there's a border between 0 and 1, a place in your code where the behavior changes. There's a border between 10 and 11, again a place in your code where the behavior changes. If you insert 10 and click order, everything should be okay. If you insert 11 and click order, maybe you get some kind of message saying, hey, that's super illegal, you are not allowed to do that. Please go away. Right, so a change in behavior. If I insert 1 or 2 or 3 or 7, click order, I would expect basically the same behavior. That the order is completed and is done so successfully. So we can talk about borders in our code here. Usually, well, often it's when we talk about ranges. As I've done here, the range 1 to 10 is legal. You might need in your semester project to create a user for your system, and you might have a requirement that a username is not 0 characters long. 1 character is often also too little, so let's say between 3 and 14 characters, for example. And you would click OK, and if you have inserted a valid username, that would be fine. So again, we have a border where the change in functionality happens between 2 and 3 characters, and between 14 and 15 characters. And everything between 3 and 14, we can expect that to be within the valid range, so there's no change in behavior amongst those. You know about the array list. There's a border when it's empty, meaning that some of the methods behave differently when it's empty. Some of the methods, well, most of them behave normally when it's partly full, and then something that you may not know, but the array list can sort of be full, and when it is full and you add another element, something extra will happen. It will actually double in size, but that means there's a border here between the maximum number of elements and the next one where we have some special behavior. So again, if I just insert B, C, D, E, that I can expect to behave identically. When I insert the last one here, that can be a change in behavior, so we have a border. Sort of similar to the pizzeria, you can have a web shop, I can order clothes. Maybe you have a maximum number of items you can buy. Maybe some of the items can be sold out, so there's kind of a change in functionality. It might not specifically be a border because it's either in stock or not. Maybe the border can be there are 3 in stock, so you can buy 3 but you cannot buy 4, so here you have a more fluid border. Dates. If I insert a birthday, then inputted valid dates can be something we need to check. Months have either 28, 29, 30 or 31 days. So that might be a border. A valid date would be to put in 30/1. But if I put in 30/2, that would be invalid because February usually just have 28 days. So you have some border where the functionality changes. If I insert dates from 1 to 28, anything in between, that would just be okay and that would behave the same. But there is a border at the end by 28 and 20, well, somewhere between 28 and 31. And last example, which may also apply to your semester project, I have a search bar. What happens if I search for something and there is no search result? Often I see that null is returned, but that may just result in a null pointer exception. Sometimes an empty list is returned, which is slightly better because that doesn't break anything, but maybe if there's nothing returned, you could also print out, you can remove the table and print out no results found or whatever. So there can be a border between the 0 and 1. So if you return 0, then you do something special, and if you return 1, it's just the normal thing. At the other end, maybe you have predefined your table to be of size 25, and what happens if you return 26 results? Will I not see the 26th result? Can I scroll? Is an error thrown? What happens at that border? Right, so a bunch of cases where we have some kind of range, some kind of border between one type of functionality and another. Our functionality changes from one side of the border to the other. So well, sort of the general question here is for both equivalence partitioning and boundary value analysis, is do I want to test every possible input? I have sort of indicated that if I can order 10 pizzas, then inputs 1 through 10 will behave the same. So I have to test for 1 and for 2 pizzas and for 3 pizzas and for 4 pizzas and so on? Probably not. If I had to do that for the array list, well, theoretically the array list has infinite size, or maybe up until 2 billions, because that's the limit of an integer or something like that, but that would be in many cases. So we don't want to do that. The idea of this is to find some kind of heuristic for selecting good cases. And we do that using the boundary value analysis and the equivalence partitioning. And this part here also combined with, well, both of them with the branch testing. So the boundary value analysis are all about the borders. We consider start end, lower, upper, maximum, minimum, just inside, just outside, empty versus non-empty, or sort of the same, non-full versus full. So both ends of the array list, for example. So these are the cases that are interesting. This is where functionality may change. So this is our boundary value analysis, or boundary testing, as we may call it. We test the boundaries in our system. So I have a line of input values, and we have a lower bound and upper bound, and I want to create test cases around the lower bound, around this boundary. So I test with the minimum value, I test just above the minimum value, and I test just outside if possible. For the array list, if the minimum value is 0, I can probably not test with -1, but if I can, then maybe I should. So we have some tests we check on both sides of the border and verify that the behavior changes here. A very common mistake in programming is what we call a +-1 error. For example, in loops, do I iterate to the list.size, or do I iterate to the list.size -1, or is it less than or equal to? So those are what creates borders, and we need to test around those. So similarly we do that at the maximum range as well. So this is the boundary testing. We test on the boundaries. Now there's a long range in here in between, and that's the next part about equivalence partitioning. So the point is, again, do I want to test for every possible input in my array list? Right? Do I add 1 and check, okay, the size is now equal to 1. I add 2, size is now equal to 2, 3, 4, 5, 6, 7, and so on up to whatever an integer maximum is, or maybe it's a long, which is even more. So obviously I will never finish writing this test if I have to write them specifically like this. A for loop might be an approach, but still that's overdoing it. So the point here is that the behavior of the method is identical in most cases. If you can add 3 elements to the list, you would expect that the 4th element to be added that would be accepted as well, and the 5th element would probably also be okay, and the 6th. And then we have the border, so maybe I need to do the boundary testing between 6 and 7 in my case here. But everything from 2 to 5 or 6, that can be considered the same behavior. If one of them works, I can expect the others to work. So equivalence partitioning is meant to cover all these cases with just a handful of samples. I take a sample size. Maybe I just insert 3 and 5 and then check, okay, those 2 work, so I expect that they can represent the range in here, that the entire range works, both 2, 3, 4, and 5. I just take a sample test. And that means the equivalence partitioning is important, because we cannot always realistically test every single case. So I have to pick out some representatives. 1, 2, 3 cases perhaps. So if we apply that to the previous examples with the pizza, if 1 to 10 the valid values, I could just use 2, 5, and 7, for example, and see, okay, that works. Maybe the rest also works. It's a fairly solid assumption. Username with a range between 3 and 14. I could test out a username with numbers of characters equal to maybe 5, 7, 11 or something like that. So we have these sample sizes. I try to buy 3 pieces of clothes and 13 pieces, and maybe that's okay. For the birthday, again, I mentioned that days from 1 to 28, we can expect that to behave similarly, so there's no need to create 28 tests. I can just test for 7 and 13 and 17, and I seem to have a tendency towards prime numbers, but that's not intentional. You can use 8 if you want. That's also okay. And the same thing for your table. So the same idea applies again. So we test around the border, the actual border, just inside the valid range and just outside, to make sure that our behavior changes between these two and not between these two. And similarly up here, I want to check that my behavior is equal, the same between these two and not here, because if it is here, then that means I probably have a +-1 error. Maybe I have a less than or equal to, and it should just have been a less than or something like that. So that's my border retest, and the equivalence partitioning here is just that I take a few sample tests inside. So boundary testing and equivalence testing. That's our 2 approaches, and combining with branch testing. Okay, so you might have guessed this, right? The intention is to reduce a large number of test cases to a more manageable size. The idea is when we use the equivalence and the boundary testing, that we have very clear guidelines on determining test cases without compromising the effectiveness of the testing, and it provides us with an appropriate it's appropriate for calculation intensive applications with a large number of variables and inputs. Right, so it's a heuristic, it's a way to approach our testing test cases, how to define our test cases. Now I have a comment about the SOMP, because you're probably going to see this in your software engineering course, and it's an acronym, zombies. So we want to test 0, 1, many, boundary. There's some interface definitions. The last three here are a bit vague on the explanation. I think when I've looked them up, interface definitions, I'm not actually sure. This here is sometimes mentioned as exercise exceptions. Again, we might consider it just, we want to check our exceptions. Are they thrown as we expected to? And then this one here is relevant. We want to set up simple scenarios, because that provides us with simple solutions. So that is, this is a guideline, a rule of thumb when we write our unit testing. So the 0 is, what happens if I insert 0? What happens if there are 0 elements in the list? What happens if there are 0 search results? And what happens if there are just 1? So we have a border here between 0 and 1 usually. The many can be considered to cover the equivalence partitioning. What happens when there are many? And then we have the boundaries, which we have discussed. And the exceptions are usually covered by the branch testing. So this is just another approach. Maybe it's easier to remember when we use this approach, 0, 1, many, boundary, exceptions, and keep it simple. And I skipped the interfaces because I don't know. Okay, so that's the end of the first part. It got a bit long, so maybe take a break, go for a run, I don't know, play a game. But end of part 1, and I'll see you, or you'll listen to me in part 2 when we get a bit more practical and try to apply the theory that we have been through. So thank you for watching.